Hello students. This is Mr. Ikechukwu Oliako, your physics teacher for today. The topic we're looking at today is gravitational field. First of all, in gravitational, we are talking about gravity. Now, let's look at the solar system. That will help us to understand gravitational field in physics very well. Solar system, this consists of the sun and the planet that revolves or moves around it, bounded by gravity. These planets are objects that revolves around the sun. This includes the Mercury, the Venus, the Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. These are basically the planets that revolves around the sun. Types of planets. There are basically two types of planets. Number one, terrestrial giants. Why do we call them terrestrial giants? Because they resemble the Earth and they are mainly composed of rocks. Examples: Mercury, Venus, and Earth, and Mars. The second one is gas giants. Why do we call them gas giants? Because they are massive and are made up of gases such as hydrogen and helium. Examples: Pluto, Neptune, Uranus, and Saturn. Now, Kepler's law of planetary systems states that Law 1, the planets each travel along an ellipse with the sun at one focus. Law 2, the line joining the sun and the planets sweep out equal areas in equal times. Law 3, the square of the period of revolution of the planet are directly proportional to the cubes of their mean distance from the sun. That is, capital T squared directly proportional to the r cube. This in mathematical form for us to understand the law 3. Now, what is gravitational field? Let's define gravitational field. Gravitational field, this is a region or a space around a mass in which the gravitational force of the mass can be felt or experienced. Gravitational force. This is a force with which attracts all objects towards its center. That is, F is equals to mass times acceleration due to gravity. The SI unit of gravitational force is what? Newton. We also what we call gravitational field intensity. Gravitational field intensity. This is the ratio of the force of gravity to the unit mass of an object and of an object and at instant. This is also known as the strength of the gravitational field. The small g, also known as the strength of the gravitational field. The formula is G equals to F all over m. That means the ratio of the force of gravity to the unit mass of an object at instant. The SI unit is Newton per kilogram because F, which is the force, is in Newton. Mass, m, which is the SI unit, is what? Kilogram. Now, let's talk about one man that was able to explain the gravitational laws. Now, no other person like our dear beloved scientist, Sir Isaac Newton. Newton's law of universal gravitation. This law states that the force of attraction between two masses, m1 and m2, is directly proportional to the product of the masses and inversely proportional to the square of the distance r between them. Mathematically, F is equals to G, capital G, m1, m2 all over r squared, where G is known as what? Gravitational constant. Is a constant. And that value of the gravitational constant is 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square. M1, M2 are the masses. R, which is the distance r square, which is this square of the distance separating them. Now, knowing this is the Isaac Newton's law of universal gravitation. We can also go further to differentiate between gravitational constants and acceleration of free fall, acceleration due to gravity. That is our small g. Let's see the differences. Number one, gravitational constants, capital G. Its SI unit is Newton meter square per kilogram square, while the SI unit of G, that is acceleration due to gravity, is Newton meter per second square or Newton per kilogram. Remember that G is also called as what? The strength of the gravitational field. Number two, it is constant everywhere. Capital G is a constant everywhere. Whether in any place, in any region, the G is constant. But the small g varies from place to place. It is not constant. Number three, it is a scalar quantity. It is a scalar quantity. Scalar quantities are those quantities that has magnitude and no direction. So, capital G is a scalar quantity. The small g, it is a vector quantity. What are vector quantities? Vector quantities are those quantities that has both magnitude and direction. Small g is an example of what? Vector quantity. Number four, dimensionally. Remember that most physical quantities can be likened to the basic SI unit. So in dimensionally, capital G is capital M raised to power minus 1, capital L raised to power 3, capital T raised to power minus 2. That of the acceleration due to free fall, small g, dimensionally is L raised to power 1, T raised to power minus 2. That is the dimension. Now, the relationship between gravitational constant g and acceleration of free fall at the Earth's surface. This has to do with, we talked about the gravitational constant g and acceleration due to gravity, or acceleration of free fall, small g. What is their relationship? Now we're going to use mathematical form to explain that. F, remember, is equals to gmr square, equation 1. Where do we get this? Remember that our g capital M small m over r squared. This is from Isaac Newton's law of universal gravitation. Weight of an object in the Earth's gravitational force is given by what? F equals to mg. Why are we using g? Because we're talking about gravitational force. We're talking about gravitational force. We're not to use A. Equating equation 1 and equation 2. When you equate Isaac Newton's universal law, which is F equals to gm m over r squared, equated by F equals to mg, you notice that the small m will cancel out. The small m will cancel out. Left with what? The big G and the m all over the r square and the g equals to g. Now, the g which we have gotten is now equals to what? G, big G, all over the big M, all over the r square. This is the relationship between the universal gravitational constant, which is capital G, and acceleration due to gravity, which is the small g. However, recall that sometimes our small g can be F over m, that is the strength of the gravity, or our acceleration due to gravity from the weight of an object, which is F equals to mg. Make g the subject of the formula becomes F over m, or ratio of force to the mass. Therefore, I can easily say that my small g can also be what? Small g, my capital M can be also be what? G r square all over the big G. From above description, we notice that G is always inversely proportional to the arrow square. What does it tell you? That the acceleration due to gravity, when you increase it, the distance between them, or the distance that is separating them, will decrease. It is inversely proportional. It is not directly proportional. But the acceleration due to gravity and the universal constant G is directly proportional. Now, factors that affect the value of acceleration of free fall. There are factors that affect the value of acceleration of free fall. That means the small g. Or you can say, why does the weight of an object is varies? That is the reason we are looking at the weights or the factors that affect the value of the acceleration of free fall. Number one, the Earth is not a perfect sphere. However, in geography, we call the shape of the Earth geoid, G-E-O-I-D. Why? Because it's not a sphere. It's not round. It's not a circle. So, since it's not a perfect sphere, the weight of a place will vary from places to places, or the value of the acceleration of free fall will vary. Number two, altitude or height of a place also affects the value of the acceleration of the free fall. Number three, latitude or position of the place in relation to the center of the earth can affect it. That means when the position of a place differ from the center of the earth, it can tell you the exact value of that acceleration of weight of earth. That's why weights of a places differ from places to places. Number four, rotation of the earth on its axis. You know that the earth is rotating. As it's rotating, it's causing day and night. That means the weight varies as the earth rotates. The value of the acceleration varies as the earth rotates. Now, these are the four factors we just looked into. Factors that affect the value of acceleration of free fall. Let's look at what we call gravitational potential. Gravitational potential. Let me define it. This is defined as the work done in taking a unit mass from infinity to the point in the Earth's surface. That's what we call what? Gravitational potential. The SI unit of gravitational potential V is equals to work done all over mass. The ratio of the work done all over the mass. That is the SI unit. The SI unit of the gravitational potential is joule per kilogram. While mathematically, gravitational potential is work done all over the mass. But from our definition, we said it is work done in taking a unit mass from infinity to that point in that Earth field. What is work done? We want to derive that potential in relationship to what we have been discussing. Now, if you look at the mathematical form of it, you notice that the work done in respect to gravitation is gravitational force times the distance. What is distance? R. We're using distance R. Recall that Isaac Newton's law of universal gravitation is equals to F equals to G, capital M, small m, all over R square. Therefore, if I substitute this universal gravitational law into the work done and above, I will have that my work done, which is W, equals to capital G, capital M, small m, all over R square times my distance R. My R square will be cancelled by one of the R above. So I'm left with what? Work done equals to what? Capital G, capital M, small m, all over R, which is my distance. Since I'm describing my electric potential, my gravitational potential V is equals to work done all over the mass. So therefore, I will have capital G, capital M, small m, all over R divided by my small m, which is the mass. By the time I do the relation fraction, since I'm having division, I'll take the reciprocal of m to now become times. My small m will cancel the small m. I'm left with what? Work done is equals to what? The V is equals to what? Capital G, capital M, all over the R. Why the minus? The minus sign indicates that the potential decreases as the object is moved from infinity towards the earth. Or the potential at infinity is higher or greater than the surface of the earth. That's why the minus sign. However, when we are solving some calculations involving gravitational potential, we might not be required to put the minus sign. Now, quickly, let's look at what we call escape velocity. Escape velocity. What is escape velocity? This is defined as the minimum velocity required for an object, such as satellite, rocket, just to escape or leave from gravitational influence of the Earth. When a satellite is being launched or a rocket is being launched, there is a minimum velocity required for such satellite to leave this Earth if you want it to travel for space. And that minimum velocity is what we call escape velocity. Now, let's look at it mathematically. That is, for us to derive our escape velocity, we must start from the Isaac Newton's law, which is F is equals to what? G, big G, capital M, small m, all over the R square. However, recall that our work done is simply what? The force times the distance, which is R. From our above relationship, what we derive when we are trying to get our gravitational potential, we saw that W is equals to what? G, capital M, small m, all over the R square, all over R. Recall that work done is equal to the kinetic energy. How is this so? For a satellite to leave this Earth, the work done in moving the satellite must be equal with the kinetic energy, that means the energy to move it. The energy required for such satellite to leave this Earth must be equal. Mathematically, that is Ke is equals to W. What is Ke? Half mv square. M, the mass, V, the velocity. However, that velocity is now what we call escape velocity, equal to the work done, and which is what? G, capital M, small m, all over R. Equating both equations, m will cancel m. We are left with what? V squared all over 2 is equals to capital G, capital M, all over R. Making V squared the subject of the formula simply means cross multiply. The 2 goes up, becomes 2G, capital M, all over the R. That becomes our formula for the escape velocity. But assuming the body to be at the surface of the Earth, assuming we are not talking about distance, we're talking about surface of the Earth, that means our small r is equal to the big R. Then Our escape velocity will become the square root of the 2gm all over the capital R. The capital R is now talking about the body at the surface of the earth, not as a distance. But recall that our M, when we were talking about the relationship between universal gravitational constant and acceleration due to free fall, that we made M the subject of the formula, we gave us small g, the acceleration due to free fall, capital R squared, that is the earth of the surface, and the capital G, which is the universal gravitational constant. We will substitute the value of M in the above equation. We will find out that it will cancel out, and the end will give us that escape velocity is equal to the square root of 2g, small g, and then capital R. That's, we have two values for escape velocity. We have two values for what? Escape velocity. The first one, escape velocity v, is equal to the square root of 2 capital G, capital M, all over big R. While the second one is escape velocity v is equal to what? Square root of 2 small g, acceleration due to gravity, then the capital R, which is the surface of the earth, radius of the surface of the earth. Now, there's an example here for us to understand how do we calculate the escape velocity of a satellite. Example 1. Calculate the escape velocity of a satellite fired from a gravitational field of the earth with 9.8 meters per second square. Take R to be 6.4 times 10 raised to the power 6 kilometer. Solution. Remember, we are giving the big R, which is the radius of the earth, 6.4 times 10 raised to the power 6 kilometer. We are given the acceleration due to gravity, which is small g, 9.8 meters per second square. And we are looking for our V, which is our escape velocity. If you look at it, we have two formulas, but one we are going to use is what? V equals to what? Square root of 2gr. Substituting the values, we see that the square root 2 times 9.8 times 6.4 10 raised to the power 6 will give us what? By the time you use our calculator, we find the values to be what? 11.2 times 10 raised to the power 3 meter per second. 11.2 times 10 raised to the power 3 meter per second. However, when we hear of kilo, that is 10 raised to the power 3. Therefore, our final answer is 11.2 times kilometer per second. The kilo value is 10 raised to the power 3. Example 2. Calculate the potential at a point on the Earth's surface. Take the mass of the Earth to be 5.98 times 10 raised to the power 10 24 raised to the power 24 kilogram. Radius of the Earth, R, to be 6.38 times 10 raised to the power 6 meters. Of course, our universal gravitational constant, the value, 6.67 times 10 raised to the power 10 raised to the power minus 11 Newton meter per second. Since we are looking for the electrical potential, remember the value of the mathematical formula for electric potential, gravitational potential is V equals to G, capital M, all over the R. Gravitational potential, the value V is equals to capital G, capital M, all over R. Now, let's substitute our values given to us. We have our capital G, universal gravitational constant, to be 6.67 times 10 raised to the power minus 11 times our mass of the Earth, which is 5.98 times 10 raised to the power 10 times 10 raised to the power 24 kg, all over 6.38 times 10 raised to the power 6 meters. By the time we use our calculator, we find out the values to be 6.25 times 10 raised to the power 7 joule per kilogram. Example 3. Calculate the force of attraction between 10 raised power 6 kilogram mass of a load hanging 1.0 meter away from 10 raised power 3 kilogram mass of iron. Take G, that is universal gravitational constant, to be 6.67 times 10 raised power minus 10, 6.67 times 10 raised power minus 11 Newton meter square per kilogram square. Our solution. Remember, from this example, we are given the mass, that means the M1, to be what? 10 raised power 6 kilogram, M2, 10 raised power 3 kilogram, the radius 1.0 meters, the universal gravitational constant 6.67 times 10 raised power minus 11 Newton meter per kilogram square. Now, we are looking for the force of attraction. Since we are looking for the force of attraction, we're using Isaac Newton's law of gravitational constant, which is F is equals to capital G M1 M2 all over the R square. By the time we substitute our values, we notice 6.67 times 10 raised power minus 11 times 10 raised power 6 times 10 raised power 3 all over 1 squared. The values, taking the law of indices, 6 plus 3 will give us a 9. Taking the law of indices further, minus 11 plus 9 will give us minus 2. However, our answer, which is the force of attraction F, is equal to 6.67 times 10 raised power minus 2 Newton. Example 4. Determine the mass of the Earth if the radius of the Earth is approximately 6.3 times 10 raised power minus 6 meters. Take G, which is our universal gravitational constant, to be 6.67 times 10 raised power minus 11 Newton meter square per kilogram square, and take the value of the Earth's gravitational free fall, G, to be 9.8 meter per second square. Our solution. We are looking for the mass of the Earth. That means the mass of the Earth is equal to small g, which is the gravitation of free fall, radius of the Earth, which is the capital R squared, all over the universal gravitational constant, small g, big G. Where did I get this formula from? From the relationship between the universal gravitational constant and the acceleration of free fall of the Earth. Making M our subject of the formula, which is the mass of the Earth, that will give us, substituting my value, 9.8 times 10, 9.8 times 6.38 times 10 raised power 6 times 6.38 times 10 raised power 6 all over 6.67 times 10 raised power minus 11. That will give me, using my calculator, 5.981 times 10 raised power 24 kilogram. That becomes the mass of the Earth. Lastly, example 5. The magnitude of the gravitational attraction between the Earth and a particle is 14 Newton. If the mass of the particle is 4 kilogram, calculate the magnitude of the gravitational field intensity of the Earth on the particle. We are given force of attraction 14 Newton, the mass of the particle 4 kilogram, and we are looking for the gravitational field intensity. Remember, our name for gravitational field intensity is the strength of the gravitational field, which is the small g. What is gravitational field intensity? We define it as the ratio of the gravitational force to the unit mass at instant. Therefore, G is equal to F all over M, which is 40 divided by 4, which will give me our gravitational field intensity of the Earth to be 10 Newton per kilogram. 10 Newton per kilogram. 10 Newton per kilogram. God bless you. Now, let's look at another ideology concerning gravitational field. Weight of object in space. When an object is, remember when we started, we talked about solar system. We said solar system consists of the sun and the 9 planets. Now, assuming there is an object in space, when an object is on or near the surface of the earth, it experiences the full extent of the force of gravity. However, if the object, for example satellite, is launched into outer space at a distance from the surface or the center of the earth, the weight of the object decreases because the earth's gravitational force on the object diminishes in proportion to its distance from the earth. This will be clearer when we talked about weightless. What is weightless? Weightless is a sensation of having no weight experienced by a body at a particular height where the gravitational pull of the earth has no effect on the body. Let me give you a practical example. When you enter a lift, elevator, suddenly the elevator cable cuts. You are inside that elevator. The elevator will begin to fall freely under gravity. The cable is no more there to control it. Now, you as a body or as an object inside that elevator will start experiencing weightless because the earth pull on the elevator does not affect you as a body. There are not a lot of practical examples of weightless we do feel every day as we travel from the aircraft or from our buses from one places to another. Now, the weight of an object in a space. Let me give you example of what we mean that when an object is in a space, its weight will reduce because the earth's gravitational force on the object will reduce it directly proportional to the distance from the earth. That means as the weight reduces, the distance from it increases. It is directly proportional. Increases, so as the weight reduces, the distance from the earth reduces. It is directly proportional. The gravitational example 1. The gravitational force of the moon on a body is 1/6 of that of the earth. If a body weighs 6.0 Newton on the moon, calculate its weight on the earth. Given weight of the mass or weight of the moon, weight of the moon is 6.0 Newton. Now we are looking for the weight of the earth. But we know that the weight of the earth from the sentence given to us is 1/6 of that of the earth. Weight of the moon is 1/6 of that of the earth. Therefore, the weight of the moon is equal to 1/6 of the weight of the earth, making Wm is equal to We all over 6. We, making it subject of the formula, is equal to what? 6 times Wm. We is now equal to 6 times 6, which will give me what? 36.0 Newton. That becomes the weight of the earth. Example 2. The mass and the weight of a body on earth are 8 kilogram and 18 newton respectively. Determine the mass and the weight of the body respectively on a planet where the earth pull of gravity is 1/8 of the earth. 1/8 of the earth. If you look at this question, we are being given the mass and we are being given the weight. The mass is 8 kilogram. It does not change whatever the location. The weight is 18 newton. The weight on a planet, remember they were specific of the planets. Maybe it can be Mars, can be Venus, any planet. But the weight on a planet from the question is equals to 1/8 of the weight of the Earth. The weight of the planet is equal to 1/8 of the weight of the Earth. That is, the weight of the planet is equal to what? 1/8 of the 80 newton. That is the weight of the Earth. That will give us the weight of the planet to be 10 newton. Therefore, the mass is 8 kilogram and the weight on the planet is what? 10 newton. Mass does not change. Mass is constant. Remember, when we talk about mass, we said is what? The quantity of matter contained in a body. Mass is always a constant. But weight varies. Weight varies from a place to places. Example 3. The gravitational field intensity at a location in a space is fifth of its value on the Earth's surface. The gravitational field intensity at a location is in a location X in a space is 2/5 of its value on the Earth's surface. If the weight of an X is 4.8 newton, what is the weight on the Earth? So we are looking for the weight of the what? Of the Earth. Now we have two methods of solving this, but I will go with the first method. Now the first method. Recall that the weight of the Earth of the place. Recall that the weight of the location of X, that is small g, is 2/5 of the value of the Earth's surface. That means the small g, which is gravitational field intensity, is equal to 2/5 of the gravitational Earth's surface. To differentiate the one we are talking of, we use X, subscript X for the location of X. Then we use E for X surface. But what is the value of the Earth's surface? We know it's constant. It is what? 10 newton per meter squared. Now, therefore, 2/5 times 10, since our Earth's gravitational free fall is 10 newton per second, is a constant. That will give us 5. 10 divided by 5 is 2. 2 times 2 will give us 4 meters per second squared. That becomes the value of the acceleration due to free fall or the gravitational field intensity of the location X. But recall that the weight of the location X is equals to the mg, that is mass times acceleration of the location X. What is weight? Mathematically is mg. M the mass, g the acceleration due to gravity or gravitational field intensity. Since we know that can we get our mass, the mass from this relationship? Yes. The weight which we are being given, the weight of the location X is 4.8. The weight of the location X is 4.8. Divide by the as a gravitational field intensity of X, which is 4. That will give us 1.2 kilogram. Then the weight of the Earth is equal to the mass times gravitational due to gravity, acceleration due to gravity, acceleration of free fall, gravitational field intensity of the Earth, which is what? WE equals to 1.2 times 10. By the time we multiply to give us weight of the Earth to be 12 Newton. To be what? 12 Newton. However, example 4. If the weight of the satellite of an Earth surface is 400 Newton, that could be the weight. What could be the weight when it is A at a distance equal to the radius of the Earth of the surface, B at a distance equal to the 4 times the radius of the Earth from the center of the Earth, at a distance equal to the 4 times the radius of the R or the Earth from the center of the Earth. Take the radius of the Earth to be 6.4 times 10 to the power 6 meter. Solution. Let's solve the first one. At a distance equal to the radius of the Earth from the surface of the Earth, we know that the R, the radius of the Earth, is equal to R plus R. That means the 2R. 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 Weight of the satellites. We are being asked what could be the distance of this satellite? What could be the weight of this satellite on the Earth's surface if it's equal to the radius of the Earth? Remember, the value of radius of the Earth is what? R plus R. Therefore, using our relationship, the weight of the satellite is equal to the capital G, which is Isaac Newton gravitational constant, mass of the satellite, ms, mass of the Earth, which is me, all over r square. This is Isaac Newton's law of universal gravitation. But we are not going to use F. We are talking about weight. Since we are talking about the weight of the satellite, that means our F will be represented with the weight of the satellite. Our r square, which is the distance, is going to be the radius of the Earth. So the radius of the Earth, which is equal, that will give us what? 2r squared. In place of r squared, we are using 2r squared, put in brackets, then squared. So that will give us, remember that our mass of the Earth, the mass of the Earth is the same thing as when we bring it out. For example, mass of the satellite times universal gravitational constant, which is G, then the mass of the Earth all over what? R squared. Recall, this is what we know as what? Weight of the Earth. Known as what? Weight of the Earth. The weight of the Earth, WE. Because WE is equal to what? Capital G, small m, mass of the Earth, all over the R. All over the arrow squared. All over the arrow squared. Remember, we have left with what? Mass of the satellite all over 4. equating with the weight of the satellite. That will give us what? 400 all over what? 4. We end up having what? 100 Newton as the weight of the satellite on the Earth. B. At a distance equal to the 4 times the radius of the Earth. Remember, before they said equal to the radius of the Earth. Now, at the distance equal to the 4 times of the radius. That means 4r, which is 4r, 4 times the radius of the Earth. That means 4 times r plus the radius, which is the distance for it to be the weight of an Earth. 4r plus r will give us what? 5r. Using the same relationship, weight of the satellite is equal to G, capital G, mass of the satellite, mass of the Earth, all over the r square. But in place of our r square, we're using 5r. Squaring it, that will give us 25r square. The same relationship we used again, which is mass of the satellite times the capital G all over m. Capital M will give us what? Will give us the weight of the Earth. Will give us what? Weight of the Earth, which is G. MS times what? G. All over what? 25. Weight of the Earth, which is WE, all over 25, will give us what? 400 all over 25. This is 16.0 Newton. 16.0 Newton. 16.0 Newton. Now, that is it for today. I hope you have really enjoyed this topic, gravitational field. Hope to see you next time. God bless you.